Hi everyone! In today's video we're going to review a little bit about carbon, and we'll also learn a couple of new things as well. So you might recall from previous chemistry classes that carbon is in group 4A on the periodic table. We could also call that group 14. And if carbon's in group 4A, that means it has 4 valence electrons. Now, in total, carbon actually has 6 electrons. So if we draw a simple diagram of carbon, we have the nucleus in the middle and then 2 energy levels. In the first energy level, we have 2 electrons. In the second energy level, there are 4 electrons. So those 4 outer electrons are the valence electrons, and those are the ones that perform all of the important chemistry. Now we could also write the electron configuration for carbon using orbitals, sublevels, energy levels, all of that. So if you're a little rusty on electron configurations, I recommend going back and reviewing that. But we'll just briefly go over it. So carbon has the electron configuration 1s2, 2s2, 2p2. And if you add up all of these superscripts, it adds up to 6. And again, carbon has a total of 6 electrons. Now, if you just focus on the highest energy level, so that would be the energy level 2, then we only have 4 electrons in energy level 2, and those would be our valence electrons. They're in the outermost energy level. You can also draw an energy diagram or orbital diagram for this, and you can use boxes to show all of the different orbitals. So in the 1s orbital, we have 2 electrons. And remember, electrons are drawn as arrows in orbital diagrams, and they have to have opposite spin. Otherwise, electrons don't really want to be near each other if they have the same spin. So they do have to have opposite spin. Then in the 2s orbital, again, we'll have 2 electrons. That's the maximum amount that will fit into an orbital. Then when we get to the 2p sublevel, we have 3p orbitals. So the last 2 electrons are going to take advantage of that and go into separate orbitals so they can be further apart from each other. Because electrons, they would prefer to be by themselves. Otherwise, they repel from each other. So notice that we only have 2 unpaired electrons. So we might expect that carbon can only make 2 bonds. However, we know that carbon can make 4. For example, methane, which is CH4, has 1 carbon in the middle and 4 bonds to different hydrogen atoms. Okay, so how do we explain that? Well, Linus Pauling, who was a really famous chemist, he was the winner of the Nobel Prize in Chemistry in 1954 and the Nobel Peace Prize in 1963. He developed a model to explain this discrepancy. So he came up with a theory that what if we combine orbitals together to make a hybrid orbital? So it's kind of like a hybrid car, right? You have a little bit of gas, a little bit of electric, but here what he did was he combined the s and p orbitals in the highest energy level, and he created 4 new orbitals called hybrid orbitals. And he decided in this theory that each of these orbitals would have the same energy, and this would allow the 4 valence electrons to each have their own separate orbital. So he called these hybrid orbitals sp3 because he combined an s orbital and all 3 p orbitals in energy level 2. Now, so this is kind of like, let's say you have siblings, and two of your siblings have to share a room, and then two siblings get their own rooms. Well, that's just not fair. So what if you take one of the rooms and like split it up so that everyone can have their own room? That would be the ideal situation, right? So that's kind of what Linus Pauling did for electrons. He gave them each their own little room. But this also helps explain why carbon can bond to four different things. Again, it's just a theory, but it fits kind of what we know about bonding, so it ends up working out. All right, so carbon again has four valence electrons, and each of these electrons can covalently bond with other atoms. And remember, covalent bonds are bonds where electrons are shared. So for example, we can draw the Lewis dot symbol for carbon, and we would put one dot on each side of the symbol for carbon. And let's make the molecule methane. Let's draw the Lewis structure for that. So each hydrogen atom has its own single electron since it's element number 1. It's in group 1A. So what we can do is just pair up each of the different hydrogen electrons with the carbon electrons, and we get our Lewis structure for CH4. So methane, again, contains one carbon and four hydrogen atoms. The way we drew it up above, it looks like they're all 90 degrees apart, but in actuality, those hydrogen atoms, which are considered electron groups, they want to be as far apart from each other as possible. So they're actually going to arrange themselves so that they have an angle of 109.5 degrees between each of them. So down below, you can see that they're going to point to the four corners of a tetrahedron. And again, that's really just to maximize the distance between each of those electron groups, the hydrogen atoms. So let's practice drawing some Lewis structures just as review. So let's draw the Lewis structure of NH3, which is also called ammonia. And then we'll also draw the Lewis structure of CO2, carbon dioxide. So see if you can remember how to draw Lewis structures on your own first, and when you're done, we'll go over them together. So feel free to pause the video, try it out, and it's okay if you don't remember. I'll come back in a second and we'll go over it together. Okay, so let's go over ammonia. So we have one nitrogen and three hydrogens. So how many valence electrons does nitrogen have? 5. It's in group 5A. So let's just draw nitrogen with 1, 2, 3, 4, 5 valence electrons. And that fifth valence electron is going to pair up with one of the previous electrons. It doesn't really matter where that pair of electrons is. It could be on the left, the right, the bottom, the top, whichever. And then we have three hydrogens, each with their own valence electron, because they're in group 1. Well, luckily, nitrogen has 3 unpaired electrons, and those could team up with the unpaired electrons on each of our hydrogens. So what we'll do is leave that lone pair at the top alone, but we'll pair up all of these single electrons around nitrogen with a hydrogen atom. Okay, and then remember, you could also draw lines in between atoms to indicate a covalent bond. So you could also draw this with 3 lines. But the lone pair of electrons we're going to keep as 2 dots because we want to make sure that we don't confuse that with like a negative charge, for example. Okay, so let's do the same for carbon dioxide. So we have a carbon atom with 4 valence electrons. What about oxygen? How many valence electrons does oxygen have? 6. So 1, 2, 3, 4, 5, and 6. And we'll draw a second oxygen down below as well. Okay, so it looks like we have 4 unpaired electrons on carbon, but only 2 unpaired electrons on each oxygen. So I think what I'm going to do is try to pair up as many electrons as I can initially. So let's put carbon in the middle. And the reason that I know carbon goes in the middle is it's by itself and it can make the most bonds. Similar to up above with nitrogen, I knew nitrogen went in the middle because it was by itself and it could make the most bonds, which was 3. All right, so I'm just going to draw my carbon again, and then I'm going to pair up carbon with one of the oxygens, and then I'll pair up one of the other carbon electrons with the other oxygen. Okay, so we still have some unpaired electrons. Now I'm noticing that we could pair up those electrons and then, let's see, these electrons. Oh, skipping the one in the middle there. Let's see if I can erase that. Oh, it doesn't want me to. Oh no, now it just erased everything. Okay, let's see if I can redraw this. Isn't technology great? There we go. Okay, so you get the idea though. We're going to pair up that top electron with the bottom electron on oxygen. So let's redraw that. So now we have 4 electrons that are shared between carbon and each of the oxygens. Oh, there we go. My pen isn't working very well. Okay, so this is going to create a double bond between carbon and each of the oxygens. Oh, my pen is short-circuiting here. There we go. Okay, so we've got our CO2 molecule, or the Lewis structure for that molecule there. So hopefully this is jogging your memory for how to draw Lewis structures. Let's just talk about one more thing before we end the lecture here. Bonding characteristics. So we saw that carbon can covalently bond to other atoms, and one of those other atoms could be another carbon atom. So in principle, there's no limit to the number of carbon atoms that can bond covalently. So you could end up with a really long chain of carbon atoms. And this is essentially what brings us to organic chemistry. So organic molecules range from really simple molecules like methane, CH4, all the way to very complicated molecules that can contain over 1 million carbon atoms. And down below you can see a couple of different ways to represent a chain of carbons. This is actually propane, which is what we use on grills, for instance. So we have carbons bonded together, and then each carbon has enough hydrogens to make a total of 4 bonds. So the first structure here is called a ball and stick model. You can see why. And then the one next to it is just a more simplified version. This is called a space filling model. So it's trying to show the relative sizes of the atoms. and then the bonds themselves aren't represented by anything. Okay, so we'll end the lecture there. I'll try to figure out what's going on with my Apple Pencil here. Next time, we're going to discuss a little bit more about the structures of organic compounds. And we'll start by talking about something called isomers. So I will see you then.